welcome back to those who were here with us last week, and welcome to the newcomers. So today is my pleasure to introduce the second of our seminars from Mobilise-D. I'm a professor in biomechanics at the University of Sheffield, and I'm leading on the technical part of the project as part of that work package too. Mobilise-D is a 5 years initiative funded by the European Union in collaboration with the European Federation of Pharmaceutical Industries. And our aim is that of connecting digital mobility assessment to clinical outcomes for regulatory and clinical endorsement. It's a very large consortium, including a number of pharmaceutical companies, SMEs, and academic partners, all led by Professor Rochester from the University of Newcastle in collaboration with Dr. Rubenov from Novartis. We all know why we're here. So mobility is one of the issues of our aging society. By mobility, what we mean is physical mobility, so the ability to move freely and easily without assistance. And of course, the problem that we have during aging society is that it is associated with the loss of this ability. And mitigate mobility loss and its consequences is a priority for our society. And the problem that we have is that what we need is really a validated approach to measure mobility. And this is where Mobilise-D is trying to bring its contribution. So in particular, what we are interested in is the specific aspect of mobility that is associated to mobility performance. So to the ability of performing unsupervised, unstructured motion in the real world. And these are the type of observations that we're interested in if we want to quantify mobility performance. And in particular, our assumption is that mobility disability is the loss of mobility performance because it's what prevents people from performing the most essential activities of daily living. And among those, we are particularly interested in Gait. The way we decided to approach the problem of quantifying and measuring mobility performance is that of using a device that can measure data for 7 days in the real world. We are developing an approach that we will see today how we're aiming at this, that wants to be device agnostic. We have already worked in trying to define some methodologies that could drive an objective decision when selecting a specific device. But of course, we need to account for what are the minimal requirements that we want from these devices. And in particular, we have established our minimum metrological requirements as being an IMU that is capable of recording accelerometers and gyroscope data continuously for 7 days. And we have seen last week how from this data, we need, of course, a number of algorithms that need to develop and designed in order to calculate what we define as our digital mobility outcomes. If you're interested in knowing more about the algorithms that we have decided to use and how we have implemented them, please go back to our YouTube channel and listen to the recording from last week. Whereas this week, we will be really focusing on how we want to validate our approach to the definition of to our DMOs in particular for the diseases of interest for the project. Which DMOs to use is something that we will establish by first validating them technically, establishing their accuracy and reliability, and then moving to a second part of the project where we will have a clinical validation study that will establish the clinical validity of the DMOs that we will select. And among all these, we will choose for each disease the DMOs that are more informative to answers to specific clinical questions. The focus of today is really on what we consider as technically valid DMOs and the tools that we are developing to establish this technical validity. So as I mentioned already, our idea is really to keep the conversation separate somehow for what concerns assessing the device that we want to use from a metrological perspective establishing the validity of the algorithms, and in particular to do this for all the algorithms that we are developing, and specifically for the cohorts of interest. But also we must never forget the component associated with the fact that we want our solution to be beneficial for the patients and to be accepted by the patients. So if we want to have a technically valid DMOs, we need to consider all these different aspects. For what concerns the device, we will be seeing some conversations today around how we are develop a number of different tests to be used to establish whether a new device could be used to, so which other devices could be used in order to satisfy the minimum requirements that we have established. We will then discuss how we have designed a validation that needs to account for all the possible factors that affect our results. So we will be looking at measuring things in the lab to make sure that we include some known challenges to our algorithms and check their response, but we will also develop the tools to validate the algorithms in the real world and specifically on the patients of interest, both for shorter period and for longer 7 days period. In particular, during these last 7 days, we will be focusing on the effect of contextual factors and on the on elements like wearability and acceptability from the patients. For the in-lab observations, we have decided to use a motion capture system, and we will be discussing how we are implementing the procedures that will allow us to run a study that is reliable even when deployed in a multicentric fashion involving different labs with different equipments. And also we will be discussing the tools that we have developed for the validation in the real world, and in particular the INDIP system from the University of Sassari in the Polytechnic of Turin, and the Equora app developed at the University of Sheffield. This protocol is available and fully described in details in the paper that you see in this slide, but most importantly is a protocol that for us has been also part of the first submission that we had with the European Medicine Agency, where we presented this approach of clearly separating the device and the algorithms so that we could in the future replicate our DMOs also with new devices. And this approach has been we were very happy to say that the approach has been considered as technically valid from as acceptable from the EMA. And again, if you want to know more about how we went about this submission to the agency, you can find the information in this paper from Viceconti et al. So before I leave the stage to the other presenters, just a reminder that everything that we'll be presenting today is, of course, supported by the IMI, but what you will be hearing from us is just our opinion and not that of the funders. Without any further ado, I will just leave the stage to Marco Caruso now from the Polytechnic of Turin. And please use the chat if you have questions throughout the presentations, and then we will have a few Q&A sessions over the next hour and a half. So please, Marco.
Yes, can you hear me?
Yes.
Okay. Okay, hello everyone, and thanks Claudia for the introduction. Today I'm going to address the metrological characterization of the inertial measurement units. Okay. First of all, consider a simple example. We have one IMU still on a table. The signal of this IMU are corrupted by a typical amount of errors in terms of offset, less than 1 millig for the accelerometer and less than 0.05 degrees per second for the gyroscope. How much do these errors affect the position and orientation estimates if we blindly integrate the acceleration and the angular velocity for 1 hour? After 1 hour, the IMU has virtually got out of Earth's atmosphere. And don't forget that the IMU hasn't actually moved from the table. And this ground position estimate is due to the poor calibration of the IMU signals. The problem was that we did not assess our device before the use. Now, the most important question is, which countermeasure can we take to avoid huge errors in the estimated digital mobility outcomes? The answer is that we should inspect the raw signals before estimating any related quantity. And up to now, ad hoc quality check procedures have not been yet systematically implemented. In fact, the Mobilise-D algorithms are developed to be sensor agnostic, but under the hypothesis that each sensor works properly. To characterize an IMU means to perform a battery of tests in order to discover its identity card in terms of metrological performances. These tests are developed to refine the device calibration when the performance are not satisfactory, to identify potential malfunctioning devices, to compare the performance with the declared value in the data sheets, and also to check the equivalence between different IMUs. It is also possible to create a mathematical model of the errors. Remember that an inertial measurement unit consists of one triaxial accelerometer, which measures the vector difference between the body acceleration and the gravity, and of one triaxial gyroscope, which measures the angular velocity. The measurements of each sensors are corrupted by two sources of errors of different type. The first, highlighted in blue, is deterministic, which consists of an offset vector and a matrix of coefficients. This source of error can be improved by refining the calibration. The second, highlighted in green, is mainly represented by the white noise, which cannot be obviously modified. Resuming the previous example, when the angular velocity is integrated over time to compute the orientation, the errors grow proportional with time and the amount of the gyroscope bias. But when we integrate the acceleration after having removed the gravity using the orientation already estimated, the orientation inaccuracy causes an error in the position estimate, which grows with the third power of time. In addition, also the accelerometer bias error strongly contributes to the final misleading estimate. Thus, it is fundamental to characterize each IMU to quantify the amount of errors which affects each signal. We can distinguish between two levels of tests. We can perform, in fact, a complete characterization of the IMUs before the distribution to the clinical centers, but also a quick characterization, which can be executed before each experimental session. The complete characterization consists of a comprehensive battery of tests. Of course, this type of characterization is time demanding, takes about 10 hours, and requires expert users. On the contrary, the quick characterization can be performed by acquiring a single recording of few minutes. Moreover, additional equipment is required for the complete characterization. To standardize the alignment, we designed and 3D printed a case to host up to 4 IMUs. To ensure repeatability, we also developed a custom rotation plate. However, also a commercial turntable can be employed. In any case, these experiments can be executed without the need of specialized laboratories. This is the pipeline we designed to perform a complete characterization of an IMU. First of all, the stochastic component is assessed and is allowed to spot a non-working device, if any. For example, the right chart represents the expected signals of a static gyroscope, while in the red charts are represented the signals of a non-working gyroscope, which are meaningless since the IMU wasn't static. If the IMU is working properly, then the deterministic components of the errors are assessed to understand whether a calibration refinement is needed. Otherwise, the device is ready to use. In particular, this step was implemented for each INDIP, since the recalibration was only performed by the manufacturer of the sensor. Thus, a refinement was needed. We considered several types of IMUs. In particular, the INDIP, the MacRoberts Dynaport MM Plus, and the Activity AX6 were employed in the TVS protocol. And since we have a limited amount of time, I would like to present just some example of the results obtained for a complete characterization. Let's start with the stochastic error assessment by computing the standard deviation of the accelerometer and the gyroscope during 3 minutes of static acquisition. This test was repeated for each IMU of the same model. On the two charts, we can assess the distribution of the parameters under analysis for all the IMU models, and this will be done also for the following tests. Then, the gyroscope bias instability was assessed by analyzing the Allen variance, computed over 8 hours of static recording. For what concerns the assessment of the accelerometer deterministic error, we oriented each IMU along the gravity direction, one axis at a time. For each orientation, the two following conditions must be verified. The first one means that the norm should be equal to the gravity magnitude, and the second that the angular deviation from the vertical direction should be 0. The norm is defined as the Euclidean distance, while the angular deviation is based on simple trigonometric computation by comparing the ideal with the measured output. The first criteria is completely fulfilled when the average norm amounts to 1000 millig. On the contrary, the second is satisfied when the deviation angle approaches to 0 degrees. In this test, the mean value of the gyroscope was computed during 3 minutes of static acquisition. Ideally, the gyroscope offset, responsible for the huge orientation and position errors, should be equal to 0. The last test was designed to compare the ideal and the measured angular velocity output during dynamic acquisition. The ideal output is defined as the ratio between the total amount of rotation angle, which is known, and the measured rotation time. Ideally, the angular velocity percentage error should be equal to 0. To conclude, I would like to leave some take-home messages. The first is that the characterization allows to assess the metrological performance of the IMUs. Then this test can be performed with simple instrumentation in any lab and any moment. The IMUs which performances deviate from the others of the same model can be identified and discarded, or it is also possible to refine their calibration coefficients. The metrological performances of the IMUs employed in the TVS protocol are satisfying, thus contributing to the reliability of the resulting digital mobility outcomes and comparable with those of existing commercial models. And last, the knowledge of the sensor noise is needed for implementing the mathematical models such as the error propagation analysis to the digital mobility outcomes of interest. So thank you for your attention. Now, if you have some questions, I'm happy to address them.
Thank you, Marco. So just to comment on overall on what Marco has presented, as he mentioned, this is really these tests that have been developed and used here are tests that we are performing on all the sensors and the devices that we have been using in the study. And we are also using these results as a benchmark reference for what allows us to say that any device that respects the same type of metrological conditions will be acceptable for us in the future to calculate our DMOs. So this is really how we are establishing ourselves as working in a device agnostic manner. So I don't know if there are questions for Marco at this stage. Again, we will be able to comment more later on if there are more questions coming. If not, we will just move on in the meantime to the presentation from Kirsty. Javier is asking, how often do you do this characterization in practice? So Marco, I don't know if you want to answer directly or if you want. Yes.
Okay, thank you for your question. In practice, the first complete characterization is done once when we receive a new IMUs, or we develop a new IMUs, and we want to assess its, let's say, identity card in terms of metrological performances. And then before each experimental session, we acquire a single recording of static acquisition just to perform some quick checks. For example, if the norms of the accelerometer amounts to what is expected, if the and also to characterize, to assess the gyroscope offset, and also above all, to assess if the device is working properly. In fact, we perform this acquisition and then we immediately process this data, and if the device doesn't fulfill the requirements, it is replaced with another one.
And so just again, just to comment more broadly, of course, we have been really quite obsessive with what we are doing as part of the TVS, because we want to make sure that everything that will be used will be fully characterized and fully assessed. As a general answer, I would say that the problem with inertial sensors is that with the fact that they are so small and easy to drop, and the fact that they can be used for like in many experiments and continuously, is good practice to perform some spot checks regularly, just to see how the sensor is responding. But we don't expect, of course, that every time that a patient has to wear the sensor, they have to do a test. This is more something that happens in the background every other period of time. The good news from us has been that we have implemented this test using really very simple approaches for measuring both for measuring the basic essential things to implement in a spot check. And again, we have been described those in already in one paper, but we as soon as Marco's paper will be ready, we are also planning to share the software and the algorithms to implement the spot check together with the instructions on how to use it. So stay tuned in this sense, because it's I think it's going to be really beneficial for whoever is using IMUs regularly. If there are no other questions, I think we can move to Kirsty now. So Kirsty is going to talk similarly to what we have performed in terms of spot checks, but for other instruments. So Kirsty.
Thanks. Yeah, so as Claudia mentioned, we are doing a set of assessments in the lab as part of our technical validation. So as in need of that, what we need is a reference system to be able to use within the lab. So for the testing within Mobilise-D, we are using a stereophotogrammetric system. For those of you who are not familiar with that, stereophotogrammetric or SP system comprises of a set of light sensitive cameras that emit an infrared light and are able to track reflective markers throughout a 3D space. So conceptually, we normally attach these to a person and then we're able to track the 3D displacement of these markers throughout time or throughout a task itself. These are well used within human movement research and are gold standard when we're considering the spatial parameters of walking or movement as well, to the point where manufacturers determine that in ideal situations, you're able to get sub-millimeter accuracy with these systems. However, within Mobilise-D, although we're happy that this is our gold standard, we do have a little bit of a situation in the sense that we're not just using one SP system, we're actually using 5 SP systems. So although in an ideal situation, we can have sub-millimeter accuracy within this, we are aware of the fact that environment as well as the system used and its setup can have an effect on these errors, as well as the calibration outcome and the session as well. In addition, the reporting of the specific errors for the system vary between manufacturer, which is an issue with us within Mobilise-D because we have 2 different manufacturers for our systems. So in respect to, as what Marco has presented in regards to characterizing our IMUs, we want to do something similar with our gold standard within the lab. So to be able to do this, we need to develop a quality control check that can immediately report these errors. Now, when we're considering these errors, we need to consider 2 types. We have our random noise errors, which come from the electronics, which may vary slightly depending on manufacturer, but also the systematic errors, which is more based on the environment that you're using the system and its context as well. So in light of this, we developed a quality control check that takes 3 things into consideration. The first being that there's no need for additional equipment, that there's minimal burden to the operator, meaning that this check can be performed quickly before any data collection, and that there's immediate reporting of the error to mean if there's anything that we need to fix or refine prior to data collection, we can do this in a timely manner. So to do this, we use the calibration object, which is proprietary to the SP system. This is an object that comprises of multiple markers where we have a known understanding of the distances between these markers and also the angles as well. Using this calibration object, we perform two short tasks. The first being a static with the object in the center of the volume, and the second is the movement of the object around the desired capture volume, both taking a total of about 25 to 30 seconds to collect. Based on this, we can then estimate or quantify the random noise errors based on the static trial that we complete. And then using the dynamic trial, we can also look at the systematic error as well. So to ensure that we could easily promote this within the Mobilise-D study and have this immediate reporting of the errors, we've compiled all this processing and analysis into a GUI, which gives us an immediate report of the errors, but also gives us a PDF version of that report that we can then slip in with the data that we've collected, so that we have the errors there to compare between the different data. This GUI source code is available via Figshare in the link below. So in regards to the deployment in Mobilise-D, as I said, we had 5 different SP systems. Fortunately, all of them were successful in completing this quality control check for each data collection that we did. And we can see on the, sorry, one sec. There we go. On the right-hand side, we have the errors here. So we can see the errors for each of the different systems, both in the distances and the angles, for the random noise and for the systematic. And the good thing for this data collection is we found that the systematic errors were always below 2.2 millimeters for distances and below 2 degrees for the angles, which when we take that into consideration of the spatial parameters that we're calculating, such as step width and stride length, they're very minimal and fractional to those outputs. So we can clearly state that this is our gold standard, and we know the threshold of the minimum threshold that we have for its comparison. So in addition to the metrological characterization that we've completed, there are other things that we need to take into consideration when trying to standardize our gold standard. The first being the data collection itself. For those of you who are familiar with using such a system, we usually attach a number of markers to a person to be able to quantify different things from the different segments of the body. So within Mobilise-D, we refined the typical marker sets into something that was more appropriate for our data collection, which meant that we had a minimal number of markers. And we also tried to minimize any errors that would come from the placements and the palpations of these markers, meaning that they had defined positions within the participant. So after we collect the data, obviously the next thing would be to try and calculate the reference points that we need out of this. However, there's a bit in the middle that we still need to consider, which is this pre-processing of this data. And this is where things can get a little bit complicated because it usually takes some manual input and manual decision making as well. So it can be sensitive depending on the operator and their expertise as well when we're considering the labeling of these markers, any gaps that we have within the data, how we handle this, and the general data quality checks that we do. So to try and minimize any manual decision making that we need and assist in standardizing this output, we have again created another GUI which helps to take the users through those processes to try and give a minimal definition as to what our data quality is within our SP system. At the final part of this GUI, we then export the data into a standardized CSV format, which is then used to calculate the reference data, as Tekla is about to explain within her next presentation.
Thanks, Kirsty, for the introduction. So before directly diving into how the stereophotogrammetric system is used as a gold standard for the in-lab acquisition, I just would like to show you again in a glance how the definition-driven pipeline that is used by the single sensor unit takes as input the inertial measurement unit data and extract digital mobility outcomes at a walking bout level. And this was presented during the first seminar of this series. And if we want to actually evaluate how good this estimation are, we need to have a reference system that can be considered to be our gold standard. And if we want to compare things like for like, we need to make sure that also this gold standard system is going to follow in a similar way this definition-driven pipeline. So in this case, the reference system that is going to be used as a gold standard is going to be the stereophotogrammetric system. And starting from the marker trajectory, we can first identify the strides. And when we have identified at least 2 left and 2 right strides that are going to fulfill the criteria that we've established within Mobilise-D, so for example, having a minimum length and a minimum duration, we can construct what we can consider our walking bout. And from this walking bout, which is our, let's say, period of observation, we can extract different digital mobility outcomes, such as walking speed or cadence. And at this point, we can compare the digital mobility outcomes that we have estimated with a single unit to the one that we have extracted with the stereophotogrammetric system and assess how good those estimations are. And as we have just seen with the presentation of Kirsty, we can actually think of the stereophotogrammetric system as being a gold standard in terms of spatial feature for the actual very low errors that we have in position. But when we are looking at the way in which the gold standard system is estimating temporal feature, this cannot really be considered a gold standard because we don't have a direct foot to ground contact information, but we can only derive that in a direct fashion. We do have other technology that can be considered as a gold standard for this aim, which can be, for example, the foot switches, pressure insoles, or force platform. But the main limitation of this technology is that when those are used as a standalone, they do not provide us with spatial information. This issue, let's say, is overcome when we are going to use pressure mat. But the limitation in this case is that all the spatial temporal information is going to be limited to the actual area of the mats itself. So if in the lab we would like to characterize different activity that we perform in our daily life, and if you think about that, it's quite unlikely that we are going to walk just in a straight line walking, and keeping in mind that we want to extract spatial and temporal information, for example, just think about the quantification of gait speed, we need to have another system. There is none of the one that I've just mentioned, but we need to go back to the stereophotogrammetric system. So if we look in the literature, there are different algorithms that have been developed to actually estimate gait events from marker-based data. But those have been mostly validated on straight line walking and only a limited portion of curvilinear walking. So to actually, let's say, assess how different algorithms proposed in the literature to actually work on data that have, let's say, on task that includes straight line walking, but also curvilinear walking and step negotiation, what we did, it was actually evaluate how they are performing compared to the temporal information that we can directly detect from pressure insole data. And what we have observed is that all of these methodology were either anticipating events, delaying them, or introducing extra events or missing some of them. So based on this observation, we have proposed a new methodology that combines an algorithm that has been already described in the literature, but has some limitation like anticipating or delaying the relevant gait events. And we are refining the identification of the gait events using 3D information of 3D velocity information of the foot. And we can also refine this gait event detection when the foot to ground contact is going to happen either in forefoot or in rear foot. We have submitted the paper, which is currently under review. So I'm just going to let's say, quickly spoiling a little bit of the results. So in this slide, you can see just the mean and standard deviation of the error that we get over 1,000 of gait events for young healthy adults in 3 walking condition. But you can see that also when this method is used for people with mobility impairment, the errors are very low. So although the paper has not been published yet, we have the MATLAB code with some data that is already available on Figshare. So please go online and download the code and start using it. So now that we have, let's say, our refined methodology for detecting the gait events from market data, we can say that our stereophotogrammetric system can be considered as a gold standard in the measurement that we are taking in the lab. So what else can we extract from this market data? So what else can be learned from this? So again, if we are going back to what was presented during the first seminar of this series, we've seen that within this definition-driven pipeline, in one of the steps, we also had the step length quantification. This can be done in different approaches, and in one of these, we also have biomechanical models. And these biomechanical models uses anthropometric information to actually estimate the displacement of the foot, having information about the displacement of the pelvis using the information of the inertial measurement data. And this kind of model has been, proposed looking at steady state walking. In this case, specifically the people who are walking on a treadmill. So for the steady state walking, we can actually assume that the displacement that we are looking at, the displacement of the foot, is going to represent exactly the displacement of the pelvis in the same instant of time. So if we are going to calculate the walking speed either from the feet or from the pelvis, the quantification is going to be exactly the same. And in particular, for Mobilise-D, the walking speed is going to be calculated as the average stride speed. And similarly, we can quantify the same information. Instead of using the stride length, we can use just the displacement of the pelvis. So we are going to characterize how quickly the pelvis moves for each stride. Nevertheless, if we are going to look at how the body moves, let's say in curvilinear walking, we can see that there is a clear difference between the displacement of the center of mass and what the internal and external feet are doing during curvilinear motion. So are we still sure that we are comparing the same thing? So for actually trying to answer this question, we use just market data, in particular the trajectory of the marker on the feet and the one on the pelvis. We've used the methodology for the gait event detection that I've just quickly described. And we have quantified the walking speed in 3 modal tasks, including curvilinear portion with turns with different magnitude and different directions. And what we've noticed is that the walking speed that is going to be quantified either from the feet and the pelvis is actually different. It's not dramatically different, but there is a difference there. So let's say that from this point of view, we can have 2 main take-home messages. The first one is that if we are going to use a biomechanical model for our single sensor unit, we are going to expect higher differences, both in length and velocity, for this curvilinear portion. And also this kind of information can be also used to further adjust biomechanical models that at the moment are for curvilinear portion. And in general, we can use this information to study the curvilinear motion per se. And hopefully we are going to present these results into international conference this summer. So now I'm happy to take any question, both for my presentation and Kirsi's presentation as well.
Thank you, Tekla. So again, just as an overall remark, these are like what Tekla and Kirsi have been presenting are really things that somehow we always gave for granted in the gait analysis world, whereas it's when we started comparing data between labs and comparing data from motor tasks that are just not simple standard gait, it really, everything becomes trickier. So it's not just for the single sensor that we need to consider all the complexity of what we are trying to do, but it's even when we use tools that we have been using regularly, thinking that they will do the job just as they come. In reality, there's been a lot of work in making sure that, again, the data that we will be using that for our final validation will be accurate, reliable, and trustworthy, and to set up the boundaries of what is that we can or cannot do with the different algorithms and approaches. And again, I hope you might have seen that while they were presenting, we have been posting the links to the implementations of the tools that we have been presenting. So of course, we would really encourage everyone to have a look and try and use them if they are motion capture users, because they can really they can hopefully be useful to help, especially in the context of multicentric trials. And so I don't see questions coming through the chat at the moment. So I think we can move on to the next presentation, which is from Francesca. Who is going to present the work that has been done for the gold standard systems that we use in the real world this time. So when we go, as I said at the beginning, we use the lab to induce trouble to the working of the person, but in reality, we don't think that that is enough. And what we want is an assessment that goes beyond the doors of the lab. So, Francesca.
Thank you, Claudia, for the introduction. Before getting to the heart of the topic, it's important to know that for an out-of-lab validation, we need a completely wearable system, which is robust and accurate enough to be used as a reference to test other technologies, so a wearable gold standard. Ideally, a system like this should include a sensor technology able to provide a direct measure of foot-to-ground contacts, which are the basis of gait analysis, since the definition of the gait cycle and all its phases depends on gait events detection. Moreover, it should have a redundant sensor configuration to improve classification and estimation accuracy, should be easy to be integrated with the third-party devices, and it should give the possibility of implementing different metrics and digital mobility outcomes definitions. In particular, for the last two requirements, we need a kind of white box, so a fully transparent, accessible, and configurable system in order to easily assess to the logic and the inner components and satisfy all the project requirements. And that's why a commercial device was not suitable for this project. And with this in mind, we developed our homemade multi-sensor wearable system, which is called INDIP system, to be used as a reference out of the laboratory. It includes magneto-inertial sensors, with a frequency of 100 Hz, which are positioned on feet and lower back, 2 pressure insoles, each with 16 sensing elements with a frequency of 100 Hz, and 2 distance sensors with time-of-flight technology with a range of 0.2 meters and a sample frequency of 50 Hz. But what does the HINDIP measure? Maybe you are more familiar with the signals in the upper part of the plot, so the accelerometer and gyroscope data, which are the output of inertial sensors. But in this case, we also have distance sensors and the pressure insoles. And from the last ones, you can see how clear is the impact with the ground. So you can already understand how those sensors are going to be used. And so starting from these signals, our aim was to extract the walking bout digital mobility outcomes, applying the same definitions used for the single sensor algorithm and also the same logical order, as already said by Tekla for what regards the SP system. In light of this, the HINDIP algorithms were developed according to the here presented flowchart. So starting from the pre-processing phase, also for the HINDIP as for the single sensor, the raw data pre-processed. In particular, the vertical component of each raw variable is reoriented along the gravity direction, and signals are filtered to improve the signal to noise ratio. The same occurs for the gait sequence detection, where the aim is to keep only the signal portions in which the subject is probably walking, and in case of HINDIP system is called dynamic activities recognition. The HINDIP algorithm for this phase is based on lower back and feet inertial sensors. So it takes the assumption that both lower back inertial sensor and at least one of the feet inertial sensors should be active in case of gait. And so for each body segment, the total standard deviation is computed starting from the linear acceleration. And then a threshold is applied to obtain 3 flags indicating when each segment is active. Finally, the 3 flags are merged in a unique flag which indicates when the subject is supposed to be walking. At this stage, all the steps needed to identify the walking bout and the relative DMOs are applied to each of the detected sequences. This process starts from the identification and selection of strides, but first it is necessary to extract the temporal and spatial parameters to define them. For the HINDIP, we start with the gait events, which are detected exploiting the redundancy of the system. In fact, both signals from pressure insoles and the feet inertial sensors are considered. The gait events are identified using 2 different algorithms and giving priority to pressure insoles in case of events detected with both methods. The algorithm based on inertial sensors is an optimization of that developed by Troianello and colleagues for the ankle positionings, while the pressure insole algorithm was developed by me and validated against 4 platforms. It is based on the activation of spatially closed groups of sensors called neighborhood. Spatial variables are estimated using feet inertial units. This step is based on the algorithm developed by Troianello and validated in Bertoli, which uses a direct and reverse integration approach to obtain velocity and displacement. In this case, the cyclical nature of gait was exploited to reduce the integration error, and the zero velocity update technique was applied to obtain the integration instance. The Madwick filter was optimized for gait and implemented by Caruso and colleagues to compute a more accurate orientation estimate. Moreover, to maximally improve our dead reckoning implementation, we performed a sensitivity analysis to optimize each of the relevant parameters specifically for analyzing gait. and improve our estimates of spatial variables. At this stage, we have both temporal and spatial variables, so we are ready to define the strides as the interval between two consecutive initial contacts of the same foot. Then the two strides are selected by applying thresholds on the minimum duration, minimum length, and maximum height to discard all the spurious movements which do not satisfy the criteria. In this phase, we also use distance sensors as stride counters. Now we have all the strides, and it's possible to identify the walking bouts. And so for the INDIP, this process starts from the strides detected with the right and left foot, and we combine them in sequences separated by short pauses, lower than 3 seconds. Then we merge the sequences of right and left strides based on temporal correspondence to obtain the walking bouts. Inside the walking bouts, we also detect the curvilinear portion with the same algorithms used for the SP and the single sensor, which is the one from Helgoari. Finally, we obtain all the relevant DMOs. This was the algorithm, but the INDIP system was not directly used for the technical validation study. It was first validated against the SP system with the preliminary acquisitions on 20 LT subjects at both the University of Sheffield and Sassari, and only after its validation it was used on patients. Now I'm going to give you just an anticipation of the results obtained on young healthy participants. And here you can see this table, which summarizes the results obtained at walking bout level, averaged across all subjects and tests. As you can notice, the error obtained for the average duration of the walking bout is lower than 1%. The error for the total length is lower than 3%, and for the walking speed is lower than 2%. And also for the other parameters, the errors are very limited. As regards the TVS, we already processed the data, and the results seem to be encouraging, but of course we cannot expect exactly the same numbers, but anyway, I don't want to spoiler anything, so if you're interested in having more details, you can just attend the webinar on April 6th. Thank you for your attention, and if you have any question, please ask me.
Thank you very much, Francesca. So I expect a lot of questions and comments on this one. This is, of course, one of the big developments, again, that we had to do to make sure that we could perform things the way we wanted. There is a first question from Udeni. I'm not sure whether Francesca or Marco, because I know you have been both working on this part of the development. And the question is around how is around the sensor alignment along the vertical axis and how this is performed in the pre-processing step. I'm not sure if Marco or Francesca who prefers to take this.
It's the same, I think. Marco, do you want
Francesca, then.
Okay.
We perform the alignment
accelerometer when we test during the characterization. So it is based on the trigonometry computation, which compare the ideal and the measured output. So in practice, we compute the inner product of the normalized vector. The expected one is the sensor was aligned along the vertical direction, and the actual measurement output. And we can compute both an angle and an axis to rotate the measurement. So we can carry out the computation using both quaternion and rotation methods. I don't know if you have another, if you want me to add another details.
I guess, Marco, if you can please share the link of your paper about the orientation, that would be really useful.
Yes, of course.
Are there other questions about the INDIP system and how we are using it? If not, I think we can move to the final part of the last bit of tools that we have been working on to make sure that everything is controlled and measured while we go to the real world. And in particular, in this case, what we have been working on is understanding what are the factors that can affect our measures that are more associated to the context in which the walking happens and the monitoring happens. So I think Neil is the first one. So Neil, please.
Okay, thank you, Claudia. So I'm going to discuss the contextual factors, as Claudia said, which are basically the factors in the real world which affect walking speed or mobility. So the first thing that we did is to come up with a selection of factors and try to determine what the importance of those factors were, so we could work out which ones to focus on. So there was a questionnaire, and it was responded to by clinicians and technical experts. And from this, the confounding factors were ordered, and then we focused on the ones which were deemed most important. This ended up with us collecting 5 factors with some sub-factors. So basically these are whether the individual is indoor and outdoor, and when they're indoor or outdoor, we had some typification of the places that they were in or the journeys that they were taking. We looked at whether people were on the same path, so they were on the same journey, to determine if we could use those for context and also comparison of how they did on that journey. We looked at the changes in elevation on their journeys, the weather as to where they were, and whether they were using a walking aid or not. So these were generally collected using GPS signals to work out the locations of individuals. With walking aids, we also used beacons. And most of the contextual factors also involved different degrees of background data to do the calculations. We didn't include two of the factors which were deemed low priority, and also the means of collection also meant that they were not necessarily going to be collected very accurately. Although we did develop technologies to do these 2 things, they were not used in practice. So the basic approach was the data was collected by the user using the phone and beacons. That data was securely sent into the Sheffield University environment where it was secured. We then did the processing of the data, adding the background data and the third-party data, and then that information was converted into an anonymized form and output onto the Mobilise-D eScience platform to then be added into the processing pipeline to be combined with the other sensor data. So we're initially going to talk about how the data was collected, and for this point I'll hand you over to Fabio.
Thank you, Neil. So hope you see my screen. What we did is we collected data for the contextual factors through mobile phones. So we use an application that we've developed over the years. It's called the Core app, and we use one specific model of a phone that was a Samsung S9. I will mention in a moment why. The algorithm behind the Core app was used to track around 1 million people in the past, so it's a rather robust technology. And what we measure are a number of variables, but the most obvious ones are location as GPS, location and network location, steps activity, so if they're walking, they're cycling, or what they're doing, and the use of walking aids. We use mobile phones and we use Bluetooth beacons attached to the walking aids to detect the presence of the walking aids. And then the phone, what the phone does, it collects the data and then uses classifiers, a cascade of weak classifiers to fuse and clean the information, and to create aggregates that are trajectories, or if you like, walks that people take. And then we quantify and qualify these segments in terms of walking speed and so on. We do it using the mobile phone sensors that are not as good as the others, but we still do it locally. And then the data is sent regularly to the server. It's typically sent once a day or every time we recharge the phone. This is the Quora app. The Quora app has a number of programs you can subscribe to, and each program requires the inputting of some information. In the case of Mobilise-D, it's just the inputting of the patient ID and the connection of the walking aids. Other applications have different types of information, and the Quora app enables to set up targets if we want to talk with it. We want to provide targets to the user, for example, mobility targets. We don't use them in Mobilise, and it also enables to collect symptoms. Again, we don't use that in Mobilise. We use it in other applications. There is also a wearable app connected to Quora that enables to collect symptoms again, just because the phone sometimes may not be close to the patient, but if they are wearing a watch, this is with them. And it also enables to record the medicine, the intake of medicine. This part is particularly done in collaboration with the Newcastle. And also the wearable can collect other variables, like, for example, heart rate. And then there is a set of tools. A set of tools are provided to the researchers when the phone is returned by the patient. They can check the compliance of the actions of the patients, if there is any compliance in terms of targets. Also, they can check if the data has been completely sent to the server, in case for sending data to the server before dismissing the patient. The moment you dismiss the patient, the entire data is erased from the phone, so that next time you give it to another patient, you don't have any data on here. So why do you want to use mobile phones? The reason is that, well, they are rather general purpose. They can be programmed. They have lots of sensors, and they have considerable battery. This is a really good advantage. And they are also familiar to the users, because we have noticed that, for example, providing a wearable like a smartwatch is not as easy with the patient. You can, of course, use consumer wearables for the same thing, and they are also programmable if you use iOS or Wear OS. They are like mobiles, but their battery is typically dreadful. So it's very difficult to have a battery that lasts for more than a day often. You can use other types of consumer devices that are non-programmable, like a Fitbit. In this case, the problem is that the data collection is fixed, so the variables are fixed. You get what you get. It's very difficult to detect contextual factors with them. For example, location is generally not available. And also they require sending data to an external company sometimes. This is not acceptable to some ethics committees. Then you have to think about Android versus iOS. Well, ideally, if you want to use the devices of the patients, you have to cover both. We cover both with the Quora app, but we focused on Android here because Android allows easier detection of variables. So iOS is much closer. On the right-hand side, there is an image provided by Radarbase, and it tells you which variables you can collect with Android, which ones you can use in iOS. We can actually collect more than those variables in iOS, but it gives you an idea of a closed system with respect to a completely open system. Then the second question we had to decide about was, do we use the patient's phone or do we use project phones? In principle, bringing your own device is best for scaling up. The problem is that different models provide different performance. Some phones, some cheap phones provide data effectively, is not viable. On the right-hand side, there is an image of a test of a number of phones, quite old phones, and you realize that some of them just collect the minutes of walking that are kind of random, 60 minutes when the patient walks 50 minutes and so on. That brings a potential inequality due to either disposable income, but that's generally not the case. People with not a high disposable income tend to have good phones, but also especially along the digital divide. Elderly people tend to have phones that are old, and especially they are not as performant as others. So project phones are an expensive solution, but it's quite good because you're in total control. You can have a standardized output, and they can be locked to specific operating system versions. This is also important, we'll see later. And you don't have strange surprises about the fact that people have incredibly strong battery savings mechanism that can stop your process, or maybe they turn it off at night. This is another thing that patients tend to do, especially the elderly tend to do. You want to have a phone that is in complete control. Clearly, what we do, we collect highly personal data like GPS data. Some other infrastructures don't do that. Again, I mentioned database, they don't do it. They obfuscate the starting position. They provide all the data as relative to that. But with that, you cannot collect contextual factors like the incline. So where people walking uphill or downhill, if they were indoors, outdoors, and so on. So this kind of that would have not been possible for us because we wanted to collect those kind of contextual factors. So what we do, we separate the data so that on the server where we send the GPS data and the personal data of this type, there is no information about the patients. There is just a single unique identifier. This is a completely separate server. The researchers who have access to the confidential information of this type don't have access to the patient data at all, so they don't know what they are. And when the contextual factors are computed, they are anonymous, and therefore they can be sent back. So they don't contain any personal information anymore. Then there is the security of the data. Of course, the server is very secure. The first lesson of security is that you never tell what the security measures are, but in principle, the data is encrypted during transmission. A secure protocol is used. Before sending, you check the certificate of the server to be sure that it's really the one and you don't have man-in-the-middle attacks. The server itself is protected against flooding attacks. And also the mobiles just send the data but never receive any confidential data so that nobody can ask the server to send confidential data. But these are just some of them. So when we want to connect, I said that one of the contextual factors is to use walking aids. So we use beacons for that, and very simply, you just scan a QR code, it connects it, and immediately the mobile recognizes that that is present, that is moved. It has an accelerometer, so we know that not only it is present, but it's also moving, so that you don't just walk nearby and you think you're using it. There was a lot of issues about how do you connect this securely. In the end, I think we ended up just taping it because there were lots of other ways, but this was the simplest one. And then there was a lot of discussions about how to charge. For example, it may seem very simple, but especially with a USB-B connection, sometimes patients are not able to connect it. We use the USB-C, but it's still, so we thought that providing a contact charger, wireless charger, was a good idea. Then we discovered that we had to put those two yellow stripes on it because people had to position it in a specific way. But still, we discovered that for some patients, this was rather tricky to do, which was very surprising. Protection, we had to provide full protection to the phone. And there are lots of other things. So the first question you may have, did people charge the phone? Did people bring the phone with them? We had one user who turned it off for privacy reasons. They didn't want to be tracked. One group of users were not told to charge the phone, and because it is not your phone, you don't check it. It was completely black to them, so they didn't charge it. So we lose the data after a few days. But nobody stole the phones, and for all the rest, we had the data. One of the problems you have with phones is the obsolescence. So we started with an S9. And in a few years, now there is S10, S20, S21, S22. You cannot buy the same phone anymore. So if you need to replace a phone, you don't get an S9 anymore. And this is one of the problems you have. There are problems with the operating system updates. We locked it, but if you buy a new phone, you won't have Android 9, you will have maybe Android 12. So there are lots of issues in keeping up with the changes, especially done by Google. And well, I'm not going into the details, but this is one of the things you have to take into account. So now I'm passing the the floor back to Neil.
Okay, I'll talk through the last part of the talk, which is to outline each of the contextual factors and the issues we had with them specifically. So the indoor-outdoor is basically collected using the GPS signal. So we determine stay points, which is the clustering of points where people are deemed to be not moving, to be stationary. And then the journeys are basically movements between those stay points. So indoors are determined by whether a stay point or a journey is identified as being within a building. And we do this by mapping the points onto the data we get from a map, primarily OpenStreetMaps. And then we can also typify those locations, whether they are residential or social or retail, etc. And with stay points, we can also look at whether they are specific to that user. So are they their home, or are they where they work, or do they appear to be those places? In outdoor is these places which are indicated as not being within a building, and the typification of this is whether people are within green spaces or urban spaces, etc. The issues that we found in Mobilise-D are how we determine that a person is stationary. Obviously, for slow-moving patients, this is maybe not be the same as the general population. GPS noise, which is basically just an issue with GPS, whether we have occlusion or reflection of the signal. Obviously, for this, we need to have a mapping data, and so we're reliant on this third-party data to be annotated and updated for each of the locations and each of the types of those. And data sparsity, which is again a issue in general with the data, that in order to make inferences about locations people visit, we need to get them to visit those locations multiple times. So within Mobilise-D, the trial was only 7 days, which in terms of the data that we've had before, we've collected data for months and months for people. So it was a little bit of an issue. So the common paths contextual factors is basically to assign the GPS traces onto actual paths on the map, so pathways or streets, and then we can determine whether the person is traveling on the same paths multiple times. Again, the issues is the GPS noise, but also the fact that potentially the paths may not be in our mapping data. This is particularly for walking paths, which are not always mapped. Streets generally are mapped quite well, walking paths not so much. Also, there's errors with the assignment algorithm that we use to assign the GPS trace to paths. This could potentially be incorrect, and the sparsity issue again. For elevation, we used country-specific elevation data, which generally is more accurate or has lower granularity. And for the worldwide data, we used something from the States, which provides a granularity about every 30 meters. So in terms of the issues with this data, those elevation data always comes with noise. Less so for the country-specific data, but it's not so much an issue in our case because we're just dealing with elevation change rather than absolute elevation. So, so that's one. And also, for people's journeys, we smoothed the elevation. The other issue is with short walking bouts and long walking bouts. So for short walking bouts, the change in elevation, the error caused by the change in the elevation is relatively greater. However, for longer walking bouts, it may be that the people's journeys may change. They may go up and down during that journey. So they're not. So it's we provide the elevation as a single value in terms of slope, but obviously for longer walking bouts, that may not be completely accurate. For weather, we determined the location of everyone during each day, the mean location, and then assigned the most proximate weather station to that. And then that weather station provides standardized measurements for temperature, precipitation, wind speed and direction, snow, etc. The principal issue with this is the limit in the stations, and that limit changes from country to country. The little image on the right shows the weather stations in the UK. And as you see, there are very few weather stations in South Wales. So if we have an individual in that thing, it could be that the nearest weather station is over 50 or even 100 kilometers away from where they are. So finally, walking aids, which Fabio talked about, which are where the beacon sends the data to the phone, so we can work out whether someone is proximate to a beacon attached to their walking aid and also moving. The principal issues with this is that we, particularly when people have multiple walking aids and which they share with their spouse, we don't necessarily know whether they're using their walking aid or walking with their partner. And again, data sparsity. There are a limited number of people in the Mobilise-D trials that have the walking aid or use the walking aid, and obviously even further limited by these people not taking very many walking bouts. So in general, the lessons that we learned from the from this collection is it was an issue not to have a continual GPS signal. For instance, if a patient was moving but they had no GPS, we couldn't differentiate whether this is because the phone was on charge in the house and the person was walking around the house, or the person was walking elsewhere and they'd just forgotten to take the phone. So it would be nice to have continual signals, and the solutions to this would be to use the patient's app, which generally people always have their phone with them. So we could assume that, or to have a bespoke GPS device, maybe attached to the IMU and then attached to the patient. But as we've discussed previously in the talk, there are issues with both these approaches. To collect the contextual factors, we rely on third-party data, and this has variation. So we need to understand the variation and to be able to deal with it. Missing data, noise, variation in precision and quality, and also the variation caused by different locations. But however, it is pretty amazing that we have this data. Basically, we have worldwide mapping data, elevation data, and weather data now, which is astounding. And as I've stated fairly constantly, data sparsity is an issue. So to assess the importance of a contextual factor on real-world walking speed, we need enough data points. And depending on the contextual factor, so for general contextual factors, so things like indoors and outdoors, this is not so bad. But the more specific the context, so if we're trying to map things like where the type of locations people are on or the type of journeys they're taking, then we need to collect more data because data sparsity becomes more of an issue.
Thanks.
So I'll open you to questions.
And I would add that collecting non-sparse, like sparse and many data during a COVID lockdown and all the experiences that we had to go through. I think that was just the cherry on top of the cake, probably. So there is a question from Javier for, I guess, Fabio or Neil.
Yeah, maybe.
Yeah.
So the question is, how is the GPS data anonymized? Doesn't it give the patient's address? Yes, indeed. So exactly because the GPS data cannot be anonymized in the sense of the address. Of course, we don't have the name and surname of the patient. What we do is that we have to keep that, and there is no way to do it. But what we do, we separate the access to information to the different researchers. So the researchers who have access to the GPS data and the other data collected from the phone have absolutely no access to the data on the patient that is on the Mobilise-D servers. When we compute the contextual factors, we send the contextual factors to the Mobilise-D servers that is used by the other researchers. Then in that case, there is no GPS data anymore. It's just the contextual factors. This is indeed a problem in the sense that we have to collect the GPS data in order to compute the contextual factors. That gives away the address. Obviously, we do also an analysis of state points, so the home address becomes quite clear. If you live in a building, in a 30-floor building, that's hardly a problem. If you live in a single family house, that clearly is contextual data. So no, there is no solution in that, except from the fact that you keep separated the concerns and the knowledge of the people.
Thank you, Fabio. I don't see other questions popping through, so I guess we can move to a conclusion now. And I would really like to thank everyone again for being here with us today. I hope we gave you a good feeling of how really we have tried to set the scene in the most accurate possible way, so that we can get out of our technical validation study with high quality data to be shared with the community. Next week, in the next seminar, we will be talking about the actual protocol. So there will be more. Remember, in my initial presentation, that we discussed also the need of assessing the users and the patient's perspective in all this. So that will be part of our findings. And of course, how all what we actually asked the patients to do while we were recording with all of our systems. So that will be the seminar will be on in March. We're going to take a slightly longer time this time between the two sessions, so it will be March 9th, same day, same time of the day. The recording of the seminars, thanks for asking, they are all on the YouTube channel for Mobilise-D. And the list of the papers cited, they are all on the Mobilise-D website as well. So you should find everything in there. And if not, please drop us an email and we will be happy to share. And again, we are trying really all the, as you have seen also the GUI and all the tools that we are developing, really. We hope that everyone will find them useful. In the coming webinars, we will also discuss all the transferring of the data and the way we are standardizing the data, and again with the idea of encouraging everyone to possibly adopt our same standards, so that we can help the moving forward with this. So thanks again. I don't see other questions coming through. So really thanks to all the speakers. Fantastic job. It's really more and more a pleasure of working with you all. So we'll see everyone soon at the next seminar.